Okay, so like I said, good afternoon, everyone. We said at 10 minutes past 2 we'll be beginning. So this is Teacher Martha, and I'll be taking us through chemistry. So I request someone to lead us in a word of prayer, and then we are ready to go for our lesson today.
Okay. Good afternoon, everyone.
Good afternoon, madam.
Okay, let's humble ourselves and pray. Almighty Father, we want to thank you for this afternoon. We thank you for your love. Thank you for your mercies. We thank you for everything that you have done for us. Dear Lord, as we're going to have this lesson, we pray that may you come and help us understand whatever we are going to learn. Come and teach us, Lord, and please use our teacher so that we may be in position to learn, to add more knowledge unto what we have. We pray all this believing and trusting in Jesus Christ our Lord. Amen.
Amen.
Okay, thank you so much, Sylvie, for that time of prayer.
Welcome.
Just a small recap, can we post in the chat the topics we were able to cover this term at our different schools? Of course, I've prepared what we are supposed to cover today, but I just want a small recap on what we were able to cover in our different schools. So kindly post in the chat so that we can have a feel of some of those things you were able to cover. Okay, I'm seeing some responses: reactivity series, carbon in life, salts and carbon in life. Okay, that is interesting. Okay, reactivity series. Is everyone able to hear me? Because someone is saying they are not able to hear me.
I can hear you.
Okay, so it seems maybe, James, your network is not very okay. You can try to log out and then back. So the topic I prepared today, it seems most of us didn't touch it. So that's what we'll be looking at because it's your first topic as senior threes in second term. So that is what we'll interest ourselves in. So I request that if maybe you're not giving an answer, or even when you're giving an answer or any suggestion, kindly raise your hand so that we can have order in the room other than people unmuting and we keep getting background noise. So it will be better if you raise your hand, then we can choose you, and then we'll also be reading some of the responses from the chat. So today we'll be looking at something interesting, and I know most of us will enjoy it. So all we need to do is to pay attention, and then we'll be good to go. So is everyone able to see my screen?
Yes.
All right,
Yes.
thank you for the response. So today we'll be looking at, who can read for us the title of our lesson? for today? Yes, Ashwan?
Formulae, stoichiometry, and mole concept.
Okay, very good. So this holiday will interest ourselves in those three different concepts where we know the formulae, the stoichiometry, and then the mole concept. So as we go about those different sections, we'll understand what each of them means. But I know at least most of us are very conversant with what the formulae is, because when we're looking at the periodic table, compounds, mixtures, and then those that are looked at structures and bonds, you interacted with some of these things. So the stoichiometry, we'll look at it, and then the mole concept. Then Patricia, can you read for us the learning outcomes? And please, as they go over the learning outcomes, you can also be repeating them over by yourself so that you're able to get conversant. So I need someone to read for us. I don't know why Patricia's hand went down. And people, can we pay attention instead of posting how I use in the chat? Let's focus. Yes, Suvi.
By the end of this topic, you should be able to A. Explain the concepts of relative atomic mass and relative mole mass. B. Examine the relationship between the number of moles and the number of particles. C. Examine the relationship between the number of moles of a substance and its mass. Then, sorry, I'm not seeing clearly. Then C.
You can increase the screen. You can increase it, just zoom in.
Yeah, I've done it, thank you. Then D. Examine the relationship between the number of moles of a gas and its volume. E. Synthesize chemical formulae. F. Interpret chemical equations. G. Demonstrate scientific attitudes and values in investigating matter. I think that's all.
Okay, thank you. So those are the different things we'll generally look at, explaining the concepts. Of course, when you're dealing with something in chemistry, you need to know what does it mean and what am I going to engage myself with when it comes to that part. So since we are looking at mole concept, we expect to interact with what we call relative atomic mass and then the relative molecular mass. And then, of course, we'll examine the relationship between the number of moles and the number of particles. And then, of course, the relationship between the number of moles of a substance and its mass. And then we'll also establish the relationship between the number of moles of a gas and its volume. Then we'll be able to come up with a different chemical formulae. And also, remember the previous topics we've been looking at, since we hadn't looked at this topic, we've been writing word equations. But you realize that when we come to this topic, most of those word equations, we are going to involve them as actual reactions with their chemical formulae without using the words that we've been using the other side. Then, of course, we are going to demonstrate scientific attitudes, because you realize that most of the things we are going to look at involve chemical reactions. That means they can be done practically. So we'll need you to incorporate those attitudes of being a scientist and the values of investigating the different objectives. Okay, so let's get someone to read for us the keywords that we are going to find in this topic. Yes, Patricia. Okay, Tekino, but please Tekino, name your device the right name after reading for us.
Excuse me, madam.
Madam, should I read? Madam, should I read? Madam, are you there? Oh, madam.
Okay, please go ahead and read. I don't know who had muted my microphone.
Okay, let me read. Avogadro's number, relative atomic mass, relative molecular mass, mole, molar mass, products, and reactants.
Okay, thank you so much, Ashran. So those are the different reactants we are going to be the different keywords that we'll find in this topic. Avogadro's number, relative atomic mass, molecular mass, mole, then molar mass, product, and reactant. Then, of course, the competence, what we expect you to have at the end of the day. You will use the formulae and equations to determine the quantities of matter. People, please, I requested, let's remain muted unless you want me to mute and I have to keep giving you permission to unmute. So let's behave. If you have something to say, just raise your hand. Okay, so those are some of the things we'll have. So we have these different comments as we go about the topic. What are some of the things you prepare at home? And of course, you can give me some answers that don't appear here. Of course, we have juice, chapatis, cakes, food. What else do we prepare at home that requires us to go through certain procedures before we get the product? Anyone who can share with us anything that is not on this list, but you know can be prepared at home. So when you look at all these different things, the juice, the chapatis, the cakes, the food, all of them require different steps. For example, if you're preparing juice, who can take us through the steps of how they prepare juice, maybe at home or at school? Yes, Jacob?
Like you get the fruits, then you wash them. After you slice them into small pieces, you add them to a blender, blend, then after you sieve. You can either refrigerate or you drink directly.
Okay, thank you so much, Jacob. And then anyone who has made chapatis, what are some of the things you do when baking chapatis? Is it baking or making chapatis? What are some of the steps you take? Yes, Patricia.
Okay, thank you, madam. Okay, for me, I know first you get, let me see, a clean bowl.
and then you add in flour, and there is also baking powder, and then some salt. Then you can add some onions or carrots, and then you add water or oil, or hot oil, yeah. Then you mix it to form dough. And after that, you get the dough, I don't know, like small, okay, the size you want. Then after you roll it on a clean flat surface. Then after you put on the pan with oil. Yeah. Thank you.
Okay, thank you so much, Patricia. So that is how you can prepare dough. But you notice that when you're preparing chapatis and juice, there is something that all those procedures have in common. You realize that all of them need ingredients. You can't do it without the ingredients. And in that case, the ingredients are what we call the reactants, and then the what? The thing that is formed after you've mixed these different things together is what we call the product. So in this topic, we are going to look at how different components, which we'll call reactants, react together like the same way you hear the word reactants. That means two or more substances have to react because we are looking at chemical reactions. So when these two react, we expect at the end of the day to get a what? A product. So the food, the juice, the cakes, you realize that all of them have the ingredients, which we call the reactants, and then to give us the juice, which is a product, the chapatis, which is a product, the cakes, which is a product, and also food, which is also a product. So you realize that in all those things above, we need what? We need ingredients. So in our last statement here, we have in chemical reactions, we need to know the amount of reactants to form the required products. For example, if you want to make chapatis for 10 people, you're not going to get a whole carton which carries a dozen of those cartons. And you say, me, I'm making chapatis for 10 people, but you're getting 12 packets of maybe Azam or Supreme that you're going to make what? Chapatis for 10 people. So that means the amount of reactants is determined by the required product. What product do you want to have at the end of that day? So that is what you are going to look at in more concept. The same thing may be to ring in your mind. You realize that maybe if maybe you want to make juice for 2 people, you're not going to go and get only one passion fruit, maybe depending on what nature it is. You will estimate how much, or even in sauce. You can't have a 10-liter saucepan and you want to put a pinch of salt. So that means what you expect to react should be in consideration of what products I want to get. So those ones I'm just using everyday examples, but we are going to see as we move on how we can use different chemical amounts of components to obtain the required products. So when you go to the chemical industries, for example, maybe most of us have looked at carbon in life, and maybe you had covered soap. If you want a specific amount of soap, you weigh particular amount of cooking oil, particular amount of sodium hydroxide, so that when you mix these two, the nature of soap that you get depends on the ingredients or the reactants you had in the preparation of soap. Okay, so and I'll move to our next slide. So how many of us have heard about atomic mass, and what do you know about atomic mass? Anyone who can share with us what you know about atomic mass? When you hear the word atomic mass, what rings in your mind? It shouldn't be the exact definition, but you can try out and tell us what you think. Yes, Jacob? Jacob, you can unmute and you tell us.
Atomic mass is like the It is the mass of one atom of any element.
Okay, thank you. That's a good trial. Ashvan?
Okay. With me, I know atomic mass, according to periodic table, as the refers to the total number of neutrons and protons in a
In a what? Okay, let's hear from Nix. It seems we've lost Ashvan because I can't hear what he's saying.
Okay, for me, what I know, atomic protons is an element.
All right, thank you, Nix. Let's hear from Jackster.
Okay, teacher, according to me, atomic mass refers to the sum of protons and neutrons in the nucleus of an atom.
Okay, thank you. That is good. Okay, only those that have a different answer from what has been given, please leave your hand up so that we can hear what you have to say. Yes, Eunice? Eunice, you can unmute. And Motorola, stop writing on the screen, please.
Atomic mass is the number of protons in the nucleus of an atom.
Okay, thank you, Eunice, but I requested those with a different suggestion should be the ones to leave their hands up. Okay, so most of us have been defining what atomic mass is, and that shows that at least most of us focused as the teacher went about the periodic table topic. But she realized that our topic our subtitle today is about relative atomic mass. So in this case, we are going to look at the different things I came up with here. So of course, we all know when we're looking at periodic table, we defined what an atom is. Can someone remind me what the definition of an atom is? Let's take F1. Please, everyone whose device is not named by their name, kindly label with your name. Thank you.
An atom is the smallest indivisible part of a material.
Okay, thank you. Let's hear from Zerita.
An atom is the smallest particle of an element that takes part in a chemical reaction.
Okay, that is good. Let's hear from Wandera.
An atom is the smallest basic unit of an element that takes part in the reaction.
Okay, thank you. So all those are very good answers. So you notice that when you're looking at an atom, it's first of all, we know that it's electronically neutral and it's indivisible. That means it's the smallest. I don't know how many of us have tried to slice fruits until you get the smallest fruit that at a point where you can no longer slice that fruit, but it's the smallest. So that's what an atom basically is. It's very, very small. That's why we may not even be able to see it with our physical eyes. Because when you look at the sand particle, you find that there are very many molecules making up that sand particle. By the time you see how small it is, that means there are multiple particles that make it up for you to be able to see it. So please, Motorola, stop what you're doing. Otherwise, you'll exit our class. So I can see Benovi in the chat is saying it's the smallest indivisible particle of an atom arranged in an atomic number, electronic configuration, and chemical reactions. Okay, thank you. So when we are looking at the different things, we know that an atom is very small and therefore it's difficult to determine its mass. So in order for us to know the mass of these different substances, we compare them. And that is where our definition of relative atomic mass is going to come from. Because we have to compare the masses, that helps us obtain a mass of a particular substance. So you may ask yourself, how do we compare the masses? And I gave an example here. Are the masses of the following objects the same? Of course, you have to post your answers in the chat. So we have a dozen of oranges, a dozen of pumpkins, and a dozen of pens. Do you think the masses, if we were to put them on a weighing scale, all these would give us the same mass because they are all in groups of 12, 12? So do you expect 12 oranges to have the same mass with 12 pumpkins and then 12 pens? You can post your answers in the chat. Okay, so I can see different answers. No, they don't have the same masses. So looking at your comparison, kudos to those answers of no, no, no. At least I haven't gotten any yes. If I had, I would ask the person to tell us why they think so. So we realize that all these are in groups of 12. Which one do you think has a heavier mass than the rest? You can still post your answers in the chat. Okay, I love the answers I'm receiving. That's, pumpkins. So we find that we have different masses for each of those. So we have the pumpkins being heavier because when you look at the size of the pumpkins, it's nothing compared to the size of the orange or the pens. So therefore, the pumpkins obviously will have a what? A bigger mass or a heavier mass than the rest. So thank you so much for your contributions. Okay, so I'm seeing Timo saying the atom was divided, the atomic bomb. I thought UPAC changed the definition as they removed the indivisible. So when we are looking at an atom, our emphasis should really be on it being the smallest particle of an atom. So when you look at that particle, it is actually very, very small. So when you look at the atomic bomb, of course, depending on the different reactions that takes place within that atomic bomb, that brings about those different changes of divisibility. Okay, so we move to the next slide. And people who are writing on the screen, please behave. We are in a civilized kind of world, so behave yourselves. Okay, so we have the different atoms having different masses. Atoms of different elements have different masses. And then, of course, like I said, when we are looking at relative, that means you're comparing two things together. Because if you say someone is your relative, there must be something that brings you people together to be related. So it can be maybe your parents, maybe your uncle. There is that link that brings both of you together. So when we are talking about relative, that means we are comparing two things together or two or more things together. So when you're looking at the atomic masses of elements, we obtain them by comparing them with the mass of carbon-12. So when you're looking at the mass of carbon-12, we are comparing those two things. So for example, if I have the one for hydrogen, I'll compare the mass of hydrogen with that of carbon-12, and I'll be able to get the desired relative atomic mass of what? Of the hydrogen. So that is what we will basically interact with when we are looking at atomic mass. Just a minute. And so can someone read for us the definition of atomic mass? It's on the screen. Fingerman, if you connect again, I am going to remove you from our group because we don't want people who disorganize our lessons. Yes, Sasha?
The relative atomic mass of an element is the average mass of isotopes of an element compared to 1/12 the mass of carbon-12.
Okay, thank you. So when we are looking at relative atomic mass, we are looking at it being the average mass of isotopes of an element compared to 1/12 of a mass of carbon. So that means when we are comparing, for example, the mass of hydrogen, how many 1/12s of carbon can we obtain? That becomes a relative atomic mass. So we are comparing the amount of these different elements with the mass of carbon-12 by getting it 1/12. So when you look at the IUPAC naming, you realize that the IUPAC emphasizes that we use a scale based on carbon-12. That is why you find us comparing another element with 1/12 of the mass of carbon. And we know carbon has two isotopes. It has carbon-12 and carbon-14. I am very sure we looked at what isotopes are when we're looking at the periodic table. So who can tell us what they know about the IUPAC? What is its full description? Who can tell us IUPAC in full? Okay, there are some people saying they can't see the work. Please log out and come back in. Then, madam, I came late. So we are handling formulae, stoichiometry, and mole concept. That's the topic we are looking at. Anyone who has an idea on what IUPAC means to share with us? Okay, thank you, Arnold. It means International Union for Pure and Applied Chemistry. So that means you'll find basically this term appearing in most cases when we have to name different substances. So they use that IUPAC recommendation. So when you look at the IUPAC, it's an international union for both pure and applied chemistry. So we relate the different masses according to carbon-12. So there is a food of thought here. You can take a screenshot and think about it. Why do you think the IUPAC recommends carbon-12 as the scale for comparing the masses of different substances? So you can find out, and in our next lesson, you can let us know what your thought was on that question. Okay, so if there are no questions, I think we can move. So we have this table here to complete. And I want our thoughts. Ashvan, is it a question or you want to give us answers to what we have on the screen?
Yeah, madam, with me, I have a question.
Mm.
I met a text in a certain textbook. Textbook, sorry. It was having that thing of IUPAC and name and something of tribal name. Now, at least with IUPAC name, I've understood, but what is the meaning of tribal name?
Okay, anyone who has an idea and wants to share with us what they think? Who can share with us their thoughts on what a tribal name is? Okay, those who want to give us answers on what is on the screen for now, you'll raise your hands when we get there. But let's first help our friend understand what do we understand by the term tribal name? Because when we have the IUPAC naming and then we also have the IUPAC name, what do we mean when we say tribal name? Because at least we've understood that IUPAC is dependent on what has been decided by the International Union of Pure and Applied Chemistry. So what about the tribal name? Tribal, not tribal. Tribal name. What's the difference between an IUPAC name? Because I'm hearing people saying pardon, pardon. What is the difference between a tribal name and an IUPAC name? Okay, I can see Sasha has told us tribal is a non-systematic name for a chemical substance. Can you give us an example? That is a very good definition. Can you give us an example of a substance where you think its naming is non-systematic? Okay, Timothy, that is good. Any other? Water? And we have very many examples, even in our daily life. Carbon dioxide. Ashvan, why did you say carbon dioxide is a trivial name? Ethanol, okay, good.
Okay. It was under the tribal name and IUPAC name it was saying carbon 4 oxide. That's why I put it there.
Okay, thank you. Then dihydrogen monoxide. I think that is the IUPAC name of water, Timothy. Then caffeine, turmeric. Okay, so when you're looking at the IUPAC names, they are basically depending on what the structure looks like. That is how they name those different what? Compounds. But when it comes to the trivial name, that is the name that is given depending on the nature of that compound. It's not basically how it appears, but I don't know which clear word to use there, but at least it carries that name. So for example, when you look at water, water is H2O. On a normal day, we would say dihydrogen oxide. But when you look at its trivial name, it's what we call water. But the IUPAC name follows the structure of that compound. How is it written? And then they will give you the name from the original basis of that structure. So like Ashvan has told us, when you look at carbon dioxide, it is CO2. And we all know that it is carbon dioxide. But when you look at its structure, maybe I can share a white screen with us and demonstrate something very small. So for example, maybe I have carbon dioxide. When you look at carbon dioxide, Samsung, please don't try it on the screen so that I'm able to explain what I want to explain in the shortest time possible. But if you keep writing, I'll keep rubbing, which will waste a lot of our time. So I was still saying, when you look at carbon dioxide, how it comes about, you realize that this carbon dioxide compound here, carbon, when we looked at its valency, we know the valence of carbon is what? Is 4. And then the valence of oxygen is 2. So when you look at these two, when we are writing the formulae for carbon, you realize that this 2 that is on oxygen comes to where carbon is, and the 4 on oxygen comes, sorry, the 4 on carbon comes on where oxygen is. But because we can have something of this sort, sorry, just a minute. So for example, like I was saying, we have carbon dioxide written like that, but we know it comes from having carbon with a valence of 4, and then oxygen with a valence of 2. So that means that 2 is going to come to where carbon is, and the 4 will come to where oxygen is. And that means we'll have C2O4. But because these numbers can be reduced, that is why we say we divide by 2 here and then divide by 2 this side, which will give us carbon, oxygen with 2 oxygens. Because here when you cancelled, that 2 with that 2 gave us 1, 1. And then that 2 here cancelled with a 4 to give us a 2. So that means you come up with what? With carbon dioxide. That is why the IUPAC name tells you that we have carbon. We have a 2 here, dicarbon tetraoxide. So you have 4 oxygens and then 2 carbons. But then the trivial name for carbon dioxide is carbon dioxide because of the nature of carbon being 1 and oxygen appearing twice. So it comes from that kind of terminology. I don't know if we are together up to that point. Those people saying they are not seeing the work, please try to log out and then back in. Okay, so going back to our slide, we have, what is the symbol of hydrogen? Yes, Akram.
Capital H, madam.
Thank you, capital H. And then for carbon, who can tell us? Nix. Okay, Nix seems to be unavailable. Okay, let's hear from Mark. Mark, please unmute and tell us.
Capital C, madam.
Capital C. Eunice, I'm seeing HG, HG, I don't know for which one you're trying to specify. So we have oxygen, because hydrogen is just H, it has no G. When you write HG, that means you're going to mercury. Hannah? Okay, let's hear from Patricia. Okay, I can see some answers in the chat, oxygen. And then for sodium. Sodium is Na, good. Then magnesium. Okay, MG, thank you. Chlorine. Okay, this is good, Cl. And please always take note of the L's. The L's you write should have a bend on them, a slight bend like what you see here. So make sure when you're writing chlorine, you write capital C and then a small L with a bend on it. Then when we go to the atomic masses, what is the atomic mass of hydrogen? Please share in the chat, what is the atomic mass of hydrogen? Okay, it's 1. Good, then when we go to the atomic mass of carbon, atomic mass of carbon is 4. Thank you. Then relative atomic mass of oxygen. I'm seeing some people with 6. 6 is atomic number. So please don't confuse those things. Make sure you know what atomic number is and what atomic mass is. 16, and at least I gave us a hint. Look at your periodic table. Okay, then for sodium, what is its atomic mass? Atomic mass of sodium is 23. Then for magnesium, what is its atomic mass? So the atomic mass of magnesium is 24. And then what is the atomic mass of chlorine? So the atomic mass of chlorine is 35.5. So atomic masses, you derive them from the periodic table. And in most cases in your exam, they will give you in brackets those different atomic masses, like we are going to see as we go to atomic relative molecular mass. But when you're looking at the relative atomic masses, these atomic masses, like I said, were obtained by comparing the weight of these molecules with the 1/12 of carbon-12. So that is how we are able to get them from the periodic table. If most of you remember, your teacher gave you something like this, where you have A here and Z here. So when you look at this A is the atomic number, and this Z is the, the A is the atomic mass, and then the Z is your atomic number. I know some of us, when we reached on carbon, you were giving me the atomic number. So these two are different, and we know what their differences are. So someone is asking, Miles is asking, why don't we just say 36 and not 35.5? Like I said, remember these masses were obtained by comparing. So how much we obtain by comparing these atoms to 1/12 of carbon-12 is what we obtain here. That is why you find that all these ones are whole numbers, but this one we maintain its decimal, because those are the times it was obtained from 1/12 of the carbon. Yes, Wandera, I don't know if it's a question.
Okay, madam. When we're given that X you've put up there, we had Z to have the mass number. I don't know whether mass number is the same as atomic number.
You are given Z as?
The mass number.
Oh, sorry about that. So here we have Z, and then the A is down for atomic. When you look at atomic mass is the same as what? Mass number. So atomic mass is the same as you saying mass number. Then atomic number, like we said, is the number of what? Of the total number of protons in the nucleus of what? Of an atom. While mass compares both the protons and the neutrons. That is why it's given as the atomic mass of those different, of the different elements that you are interacting with. I don't know if I've answered your question. You had already unmuted. Okay, so yes, Patricia.
Okay, madam, the atomic mass of magnesium. Okay, in some textbook, it's showing me 24 point, of sodium, it's showing me 23.3. No, 0.0, and then magnesium 24.3. Is it that you've just rounded up to the whole number, or there's another of writing them with the decimal point.
So the basic standard atomic masses we use, even in the periodic tables that you'll be given, are those values, 23, then 24. Then for calcium, we can't, sorry, for chlorine, we can't just say 35.5 because remember 35 as, because remember chlorine exists in different isotopes. It has isotope 37 and then the isotope 35. So for it, we specify its value to be that because we are differentiating it from its second what? From its second isotope. Okay, I don't know why people are harming. I don't know if it's because they are not understanding or I don't know what is happening. Okay. But if you're not understanding, please raise your hand. And otherwise, this recording will be shared on your group, so look out for it. Mr. Kaziba will post it and please go over it because the truth is we can't go back to where we started from. It's an hour past 6 minutes since we started. So we can't really go back. But if you feel you've not understood the whole point, just look out for the video and follow through. Okay, so after getting that point, okay, someone is saying they're not understanding what I did on the right-hand corner. I'll repeat that, and I think now I'll just repeat that and then we move. So just follow through. I said when you are looking at periodic table, because I know most of us here are, actually all of us here are in senior 3. So that means we've already covered the periodic table. So you recall in the periodic table, your teacher gave you X is the element, Z is the atomic mass or atomic number, sorry, or mass number, atomic mass or mass number, which we defined as the total number of protons and neutrons in the nucleus of an atom. And then our A here is what we call the atomic number, which we said these are the number of protons in the nucleus of an atom. So I was describing for people that were giving me different values here, that when you're using the atomic mass, you look at the number that is on top of that element on your left-hand side. So the number on top is what we have here as relative atomic mass. And I have explained that we are calling it relative because it was already obtained by comparing it to the carbon-12 mass. So that means it becomes a relative mass because there was comparison between that element and the carbon-12 isotope. So I hope the person has now understood what I meant there. Okay, so someone can post the link of the group in the chat so that those who are not on the group can join. So so you can copy down this table, or when the recording is posted, you can take a screenshot even now so that you can be able to fill in those details for your own notes. It's very, very important. Because when some people switch on their videos, I see some sleeping. I don't know if they are taking notes, because it's important to be in class and take some notes that will guide your reading. So we are moving on to the next slide. And this next slide, I encourage us to be very alert so that we can understand what we are going to look at in our last slide for today when we get to it. So when we are looking at relative molecular mass, who can tell us why they think the relative molecular mass has no units? Why do you think the relative molecular mass has no units? Yes, Wanderer.
This is because relative molecular mass is a ratio.
Okay, good. So what is it? What makes it a ratio? Why do we call it a ratio? Anyone who has an idea?
Yes, madam. Let me try. We call it a ratio because to obtain it, we have a fraction to have obtained it from carbon as 1 out of 12.
Okay, thank you. Anyone else? So like we said in relative atomic mass, and in that case for it, we're just looking at one element where we said hydrogen. So we compared the mass of hydrogen with carbon 12. So when it comes to relative molecular mass, that means you're forming a what? A compound. So this compound is related with the 1/12 mass of the carbon 12 atom. So because of that comparison, that means it will not have units because you're basing on a what? On a ratio. And the things you're comparing are both in mass units. So for example, if the relative atomic mass of a given compound is measured in atomic mass units, which is AMU, you realize that if both of them have those units, the units cancel out and you're able to get a figure that has no units. So that is why we call it relative molecular mass. And then of course, when we come to ionic compounds, of course, you look in more details at those things. Most of you have already looked at them when you are looking at structures and bonds for those that have covered that topic. But if you haven't, still you'll look at those and you'll appreciate what ionic compounds are. But just to give us a glimpse, when you're looking at ionic compounds, you're having a metal and a non-metal forming a compound. So in that case, when these two form a compound, you're able to obtain what we call an ionic compound. And of course, the details, I reserve them for that topic. So I want someone to read for us this statement after therefore, what relative formula mass actually means. People, can we have other hands? Because it's the same people over and over again. Bonfella, can you read for us? Redemptor.
Relative formula mass of a substance is the mass of 1 mole of a molecule of that substance.
Okay, thank you. So when we are looking at relative formula mass of a substance, we are looking at the mass of 1 mole of a molecule of that substance. And of course, we are going to look at what a mole is in our next lesson. So when you have the relative formula mass of that substance, you're looking at how much does that component weigh when compared to 1 mole of that given molecule. So for example, if I have sodium hydroxide, I'll find out if it is 1 mole of sodium hydroxide, because if I am looking at its quantity in terms of moles, if 1 mole of sodium hydroxide, what is its what? What is its weight? So how much weight does it have? So we are going to look at that briefly. Okay, Motorola, you have a question? Okay, so someone is asking what an isotope is. Anyone to help us help our friends to know what an isotope is? Yes, Lina?
Madam, an isotope, these are two or more atoms of the same element have a different mass number.
Okay, thank you.
Welcome.
Let's hear from Patricia.
An isotope is an atom of the same element with the same atomic number, but with different mass number due to difference in the number of neutrons.
Okay, that is good. Redemptor.
An isotope is one of the atoms of an element which have the same proton number and different number of neutrons.
Okay, thank you. So when you're differentiating those two, we focus on having same mass number, same number of protons, but different number of neutrons, or you're looking at same atomic number, but different mass numbers. And that comes into play when you're looking at the different, because like I said, for example, we have carbon. We have carbon 12 and we also have carbon 14. When you look at those two, the number of atoms of carbon 12 is different from the number of neutrons in carbon 14. So you realize that the number of neutrons in carbon 14 is going to be different from the one of carbon 12. Because here, as you have the different mass numbers, when you subtract the number of protons from the mass numbers, they'll give you different number of protons. So that is one of them. And then we also have chlorine, where we have chlorine 35 and then chlorine 37. So when you compare these two, they are called isotopes because they have the same number of protons, but different mass numbers or different neutrons. Because we all know when we get neutrons, we are getting the mass number minus the atomic number. So these are what we call isotopes. So chlorine can exist as chlorine 35 and as chlorine 37. Then carbon can also exist as carbon 12 and carbon 14. So you can come up with any other different isotopes. As you make your notes, you can look out for more isotopes. So I think we've closed that chapter. Can we move on? Yes, Bonifela, do you have a question or Redemptor?
This is what my teacher gave me. Isotopes are atoms of the same element with the same number of protons but different number of elements. While an isotope is one of the atoms of an element which have the same proton number and different number of neutrons. So I'm not getting your point on what you're saying.
What did you define first? Please don't mute before I try to respond because I need to gain ground.
I defined isotopes. Isotopes are atoms of the same element with the same number of protons but different number of elements.
Yes, I think that's what we've been saying. Is it different from what we've been saying?
A bit, but I've
I think it's
understood.
just the construction that is different, but the terminologies are the same, because you have to understand that when you're looking at an isotope, first of all, the atomic number is the same. But then when it comes to the atomic masses are different. Reason being the number of neutrons is different for each of those elements. So I think it's just the construction, but the terminology should really draw you to the same thing.
Okay, thank you.
Yeah. Okay, thank you too. Patricia?
Oh, thank you, madam. Okay, like the neutron number. I mean the neutrons are they constant? Or let me say, is the atomic number, I mean mass number, constant? Or you can, okay, I don't know, but is it possible for you to have the neutrons without you having the mass number?
Anyone that can answer Patricia's question? Okay, so her question is, can you have the number of neutrons without knowing the mass number or the atomic mass? How come seeing Redemptor is saying probably, then Murunji is saying yeah. So can these people put up their hand and they tell us how we can obtain the number of neutrons without the mass number? Sorry, the atomic mass. Because, okay, I want us to understand, when you're looking at atomic mass, like you would say mass, what is your mass? And then you tell us how much you weigh. So it's the same thing when it comes to an atom. An atom has a weight that it carries. But that weight is dependent, because for example, you have the nucleus, which has a proton, and then the neutrons. And then we have the energy levels, which have the electrons of those different depending on what element we are looking at. So we said that electrons don't carry any weight. So that means we don't count the electrons. So when we are looking at the weight of an atom, we look at the nucleus of that atom. So the nucleus is what bears the what? The protons and then the neutrons. So when you have the protons, which is the atomic number, and you know the atomic mass or the mass number of that given element, that means you can subtract the number of protons from that mass number for you to be able to get the what? The neutrons. So that means the neutrons depend on the weight, which is the mass number or the atomic number, and the proton number. I don't know if I've answered your question, but that is what we use to compare. So you cannot say you're going to get the number of the number of neutrons without knowing the weight of that element. So it is about you having those two things, and then you compare, which you must at least have two to find one. The same way you may have length times W to get the area of a rectangle. So it is dependent on you having the what? Benovi, I am not very sure of that carbon-16. I'll need to find out. I know only 2 isotopes, but I can read about that and revert in the next lesson. So I only know carbon-12 and 14, but there is always room for knowledge. So I can read on that and revert. So I think I've answered Patricia's question. If not, then that is the best way I could explain it surely. So I hope I've been able to answer your question. Okay, so let's move on to the next slide. So for example, when we are calculating the RMM of a given substance, when you look at sodium hydroxide pellets, is 40, and this means that 1 mole of sodium hydroxide has a mass of 40. Therefore, its relative molecular mass becomes 40. Because remember, we said when we are looking at the relative molecular mass, we are looking at how much it weighs in consideration to the number of moles in that particular component. And please, let's stop bringing in other things to confuse others, because now when we start going into allotropes, we may stay here for a very long time. So let's just direct our knowledge on what we are covering for now. Let's not deviate from what we are covering, because now I'm seeing people starting to ask what is an allotrope. So let's really and then someone has inboxed me, excuse me, miss, I think this meeting has a bot. I don't know what that means. Maybe you can explain further what you mean by bot. Okay, so when you are looking at the atomic mass, we have sodium. Like I said, when we have 1 mole of sodium, we know that the chemical formula for sodium is Ha, and the one for hydroxide is OH. So when you look at these two, the valency of sodium is 1, the valence of a hydroxide is 1. And I am assuming we looked at these things when we're looking at the periodic table. So I keep referring us back. If you didn't understand that topic, kindly go back and read about that. So when the valencies cross, because the valency for sodium hydroxide will cross to sodium and the one for sodium will cross to the hydroxide. So we'll have the formulae, since they are all ones, the same way in math, we don't write 1x and we say it is just x. So it's the same thing here. When we have ones, we keep them silent and we just say it is sodium hydroxide. So when we have this sodium hydroxide, you realize that it is existing as 1 mole. So in this case, we find out what is the RAM of sodium. Remember, we looked at the relative atomic mass up there. So what is the relative atomic mass of sodium? Who can tell us? You can type in the chat what you think the relative atomic mass of sodium is. Mark, what is 1 supposed to mean? I don't know. Yes, Patricia. Okay, in the chat I'm seeing 23, very good. So the RAM of sodium is 23. Please follow through. And then what is the RAM of oxygen? What is its relative atomic mass?
16.
16, very good. And then the one for hydrogen?
1.
1, very good. So in this case, when we are getting the relative molecular mass of sodium, we get the sum of these 3 because sodium hydroxide is made up of sodium, oxygen, and hydrogen. So that means we'll come and say relative formula mass is equal to 23 because there is only 1 sodium there, plus 16 because there is only 1 oxygen there, plus what? 1, because there is only 1 oxygen. So when you add those 3, what does it give you as the relative formula mass of sodium? 40, very good. So that means 1 mole of sodium hydroxide weighs 40 grams. So that is how we basically get the relative formula mass or the relative molecular mass, depending on what component we are looking at. So are we all together up to that point? Let me get at least 3 responses in the chat. They will be able to guide me to follow. Okay, thank you, Mark. Thank you, Jackster. Okay, thank you, Akram and Ashba. Okay, thank you for that feedback. So we can move on to the next. The next ones, I am going to request someone to explain to us what to do. So, but before we do that, I want someone to read for us these remaining statements. The one immediately after the RMM of sodium hydroxide. This time round, I need someone who hasn't yet said anything. So that at least you also say in the lesson, I said something. So you put up your hand and you tell us. And you read for us. At least reading is very easy. Okay, Mal.
I'm reading the second point.
Up to the last one.
Okay, the relative molecular mass is obtained by adding the relative atomic mass of all atoms in the formula of the substance. Calculating the RMM is a compound of, calculating the RMM of a compound is done in 2 steps. Step 1, write the correct symbol of the compound. Step 2, sum up the atomic mass of elements present in the compound.
Okay, thank you so much, Mal. So when you're looking at those substances, remember the first thing I did, I looked at sodium hydroxide pellets, and you remember my first initiative was to write the what? The chemical formula. And that is what our first step is telling us. Write the correct symbol of the compound, then sum up the atomic masses. You remember I asked you what is the atomic mass of sodium, which we said was 23. Then we said the atomic mass of oxygen is 16. The atomic mass of hydrogen is 1, the relative atomic mass. So we added those 3, and that is what our step 2 is telling us. Sum up the atomic masses of the elements. And then you're able to get what we call the relative molecular mass. And in most cases, we authorize the RAM because the statement is quite long. And then for RFM, we said for those ionic products. So you see for sodium, sodium is a metal, the hydroxide is a what? Is a non-metal. And remember I told you that when we are dealing with ionic compounds, we are looking at a metal combining with a non-metal to form a compound. So basically that is how you come about the relative formula mass or the relative molecular mass. So you get their relative atomic masses, add them, then you're able to get the RMM of that given compound. Okay, so next we move on. So we have a slide here, and I want every one of us to get their pens, pencils, even those that were not writing, who chose to just be spectators. It's time to do something with our hands. So I'm going to give us, how many minutes should I give us to try out this? The rest we'll do after we've gotten at least the answers of these 3. So how many minutes should I give us to try out these 3? And then we get responses of people. We'll get 3 people to explain to us what they have done. And then we are able to do the remaining 2 together. Hey, who is saying 30 minutes, Banang? You want us to waste the whole lesson? Adrian, 30 minutes are very many. Okay, 5 minutes. Okay, that's good. So 5 minutes we go. Yeah, I said Banange because the minutes are very many. 30 is quite a long time. Even 10. Volch and Edda, at least create another lesson for yourself. We can't give you 2 hours to do three numbers of chemistry. So let's look at, we are using 5 minutes and I've started counting. So it is 3:36. That means by 3:41, we should be completing. Okay, so let's work on that. People who write on our screen, please style up. Like I said, we are in the kind of generation that is civilized. So behave yourself. Patricia?
Finished.
You've already finished calculating?
Mm.
No, at least let's wait for other people. Thank you. I love your speed. So you'll be the first one to do for us number 1, but let's give people those 5 minutes to complete. Because some people will just Xerox everything we are giving here. Yet I want them to first try out. But some people like Xeroxing everything. They'll Xerox from A to Z. So it's better we give them some time to also do some work with their hands. So that at the end of the lesson, they're like, yes, I learned something new. Okay, I can see some people saying, I have finished, I have finished. Okay, that's great, but let's give people some time. Okay, Akram is saying we'll do number 2. So we need someone to do number 3 and we are good to go. So we said Patricia number 1, Akram number 2, and you'll be able to use the screen because I think that setting is there is enabled where you can use the screen to show us. Okay, Motorola is saying number 3. Okay, so I'm seeing quite a number of us is done. Okay, someone is pleading for Roland. Roland will do for us number 3, and then we need someone to do for us Roman 4. So we have already the numbers taken. So that is a good thing. But let's first have those 3, then we can see how we do the rest. Okay, Redemptor is saying number 4. Okay. So I don't know how many boys I have doing numbers, but I hope it's not only one boy because you need to have all of us on board. Okay, so quite a number is done. So let's have Patricia. Please raise your hand so that I can see you, and I ask you to unmute. Then you can take us through.
Okay. Should I start?
Yes, please.
Okay. So the formula of water is H2O. That means there are 2 hydrogens and 1 oxygen. The relative atomic mass of hydrogen is 1, then that of oxygen is 16. So in our formula, finding relative molecular mass to be atomic mass of hydrogen plus that of oxygen. And then hydrogen, since there are 2 molecules of hydrogen, we multiply 1 times 2, which will give us 1, plus the relative atomic mass of oxygen, which is 16, giving us 17 as the relative molecular mass or relative formula mass. Thank you.
Thank you so much, Patricia. But I expected at least for you to write on the screen so that you show us what you did. Because it's possible for you to use my screen to write something. Because sometimes when we just talk, people are seeing stars. So it's important at least to write down something. Patricia, are you able to unmute or you have muted yourself?
Oh, I also wanted to correct somewhere. Okay, so as I said, hydrogen. Okay, madam, I'm using a small phone and it's hard for me to write on the screen. It's hard.
Okay, it's fine. I think you talk as I write for you.
Okay, thank you.
All right.
So the relative molecular mass, fraction mass, in order to find it, shall have the relative atomic mass of hydrogen plus that of oxygen. So the relative atomic mass of hydrogen is 1. But since there are 2 molecules of hydrogen, we multiply that 1 times 2.
Okay. So we have 1 times 2.
Yes,
So this is
the
the RMM of hydrogen, right?
Yes.
Okay.
Plus 16 of oxygen.
Plus 16 of oxygen. Okay.
1 times 2 is 2.
Okay.
Plus 16. So the 16 plus 2 gives us 18, which is the relative formula mass.
Okay, that is good. Is that what everyone got? Thank you so much, Patricia.
Welcome.
Okay, so please, among those people that are doing the numbers, if you find a challenge, please just let me know so that I can be able to write for you as you talk. So that is basically how you get it. So we have 2 molecules of hydrogen, because remember we said we start with writing the chemical formula. So the chemical formula of water is H2O. So we have 2 hydrogens. That means we get the relative atomic mass of hydrogen multiplied by what? By 2, because there are 2 molecules of hydrogen. And then for oxygen, it's 1. That is why we have 16. And someone else can say 16 times 1, and they're able to get their values. So that means the relative formula mass of water is 18. Wow, okay. Who did we say was doing number 2? The rest of us, please, can we put our hands down so that I can unmute the person we said was doing number 2? Okay, Akwan.
Okay, we are doing sodium chloride, right? The formula for sodium chloride, we have it as sodium having Na and chloride having Cl. Both of them have
Are you writing or I write?
Adam, I think it's better if you write. Let me. Okay, I can write.
All right.
So we have sodium as Na, and then chloride to have Cl. They all have valences of 1, like sodium has a valency of 1, and chloride also has a valency of 1. So the the relative molecular mass of sodium is 23. 23. Then the RMM of chloride is 35.5. I'm sorry for the handwriting. So we shall add the 23 plus the 35.5 to give us 58.5. Thank you.
Okay, thank you so much, Wandera. So when we are looking at, like we did the other time, we first write the chemical formula of sodium chloride, and at least we've interacted with that one because it's the common salt. Then of course we know the the RAM of sodium is 23, and the one for chlorine is 35.5. And then when you add the two, of course, they're going to give you this, the 58.5. Is it 0.5? Yeah. So that is what you will get there. And that will become your relative formula mass. But please, just because we are using this screen to maximize everything, make sure your work is in an orderly way. Like it flows. So don't just write things anyhow. So you say relative formula mass of sodium chloride is equal to, these ones are not supposed to be joined, so please don't join them. Sodium chloride, then you know the RMM of sodium is 23. And since it's 1, we leave it as is, then 35.5. And then you're able to get your 58.5 as your RFM. So when most cases, they will always give you this information. But of course, for the common elements, you may always know the values that you're supposed to use, but they always give you that information for you to use. So who did we say is doing for us Roman 3? Please raise your hand and you let me know if you're the one going to write for yourself so that we can move. What did we say was doing number 3? Okay, Jackster.
I think you'll be writing.
Oh, okay. Is it possible to get a stable network? Because I don't seem to hear you. Is anyone here able to hear Jackster? I don't seem to hear him. No, but I unmuted you. You raise your hand again so that I can unmute you, but I had already asked you to unmute.
Oh, thank you, madam. I think you'll be writing for me.
Okay.
Getting the relative formula mass of magnesium hydroxide is a relative formula of mass of magnesium hydroxide is equal to, we first write it's Mg OH. That means magnesium, the relative mass of magnesium is 24 plus relative mass of oxygen being 16 plus hydrogen 1, totaling to 41. Thank you.
Okay, thank you, Jackster. So there is something I want us to correct here, and I want all of us to focus on what it is. So when you look at magnesium, magnesium is a group 2 element. That means it has, magnesium is a valency of 2. Then we have the OH, which is the hydroxide, and this one is a radical. That means it can't exist on its own. It has to combine with something to exist. So we say this hydroxide of the hydroxide has a valency of 1. So when these valencies cross over, that means we are going to have the 2 come where the hydroxide is, not on only hydrogen, but on where the whole hydroxide is. So that means we'll have the formula of magnesium hydroxide as this. And because the 2 is taking on both elements, that is why we put brackets and put the 2 outside. So that means here when we come to the the relative atomic mass of oxygen, we are going to multiply this 16 by 2 and the 1 by 2 because of what happens in the formula of magnesium hydroxide. So are we all together at that point? So that means at that point, we are going to have our relative formula mass of magnesium hydroxide, because magnesium, we've said, has a valency of 2. So that 2 goes to the hydroxide. That means we are going to have it as magnesium. We say the valence, the atomic number of magnesium is what? 24. And because it has a silent one, for it, we leave it as is. But the oxygen, because of these 2 outside the brackets, that means we'll have 16 times 2 plus hydrogen, which is 1 times 2. So this 2 multiplies both the oxygen and the hydrogen because it's outside the bracket for both of them. So that means here we are going to have, what is 16 times 2? Someone post the answer in the chat very fast so that we can move. 32, very good. Then times 2. So here, what is going to be the RFM? What is 24 plus 32 plus 2? Okay, beautiful, 58. So that means we have 58 as the RFM of magnesium hydroxide. So I hope everyone is with us to that point. So let's have the person that said they're doing for us the last one, which is magnesium chloride. Yes, Redemptor.
Madam, I request that you help me write.
Okay, let me just drop this. Okay, I think you can start.
The chemical formula of magnesium chloride is MgCl2. And the the relative atomic mass of magnesium is 24. And the one of chloride is 35.5. But since there are 2 chlorides, we multiply the 35.5 times 2. To get 71. .5 times 2 is 71. So 24 plus 71 gives us 95. Thank you.
Okay, thank you so much, Redemptor. So like we said, magnesium has a valence of 2, and we know chlorine has a valence of 1. So when we do a crossover, you realize that the magnesium has a valency of 2, which crosses to chlorine, and then the chloride has a valence of 1, which crosses to magnesium. So that means you're going to multiply the RAM of chlorine times 2, and that will give you, when you multiply, does it give you 71? Because I saw a different answer here. Okay, so good. So you go on ticking yourself if you really did the work. If you're Xeroxing, we hope for better next time. Okay, so thank you so much. Lastly, I know our time is usefully and fast spent. I want someone to do for us the one that we should have started with, but people ran away from it. And as if someone had inboxed to do it. Was it Rowan? Please raise your hand so that you can unmute and take us through. Mark, please unmute.
We'll start with the...
Are you writing?
You're right.
Okay.
The chemical symbol of oxygen is O2. Then the relative atomic mass for oxygen is 16. Is equal to 16. Then we multiply the 2 times the relative atomic mass. Which will give us 32. Thank you, madam.
Okay, thank you so much, Mark. So that is very good. So we know that oxygen exists as a diatom. So because it's a diatom, that means it exists as O2. So that means we have the relative atomic mass of oxygen as 16. So to get the RMM, we get the 16 times the 2 to give us the 32. So that is what we obtained there. So I hope everyone was able to learn something in this lesson. And please, when you go back, read more and also try out other numbers so that we are able to catch up when we meet again. So I'll request someone to lead us in a word of prayer so that we can close. I'm seeing Patricia. I don't know if it's a question or you're praying for us.
I want to pray.
All right, please go ahead.
Let's humble ourselves and we pray. Almighty Father in heaven, thank you for today. Thank you for the gift of life. Thank you for we've begun our lesson with you and you're ending it. Dear Lord, as you are living, we pray that each and everything we have learned from here may stick into our minds, that we not just waste it. And also we pray that you may bless our teacher in each and everything she does and increase her wisdom. We have prayed less but expecting a lot from you. In Jesus' name I've prayed and believed. Amen.
Amen. Amen. Okay, thank you so much. So someone is asking if I can give questions. So maybe find the atomic. I'm going to just leave us with 3, then you can really do the rest. So find the relative formula mass of the following. Please jot down very fast. Thank you so much for that prayer, Patricia. So you can write down very fast because I'm not going to write on the screen. Thank you everyone for appreciating and thank you for connecting. So we have calculate the relative formula mass of Roman 1. Someone is asking for 10. You can look for the remaining 7. But for now, let me give us 3. Find the relative formula mass of Roman 1, calcium hydroxide. Calcium hydroxide. The Roman 2, hydrochloric acid. Hydrochloric acid. Roman 3, sodium carbonate. Sodium carbonate. So the first one, we said calcium hydroxide. The second one, we said hydrochloric acid. And then the third we have is sodium carbonate. So please try out those and we'll begin from there in our next lesson. All right, thank you so much for connecting. Have a blessed evening. See you next time. Okay, I love you two all. So let's see again next lesson. Okay, let me unmute people because now the lesson is done as some logo.
Bye.
Bye.
Bye, teacher.
Bye.
Thank you.
Bye. Thank you too.
Redemption.
Thank you, teacher.
Next time, God bless you.
Bye.
Next time, God bless you too. Please make sure you're able to remember what we've learned and also
Yes.
read further. It's very
Bye.
important.
Bye, madam.
Bye.
Bye.
Bye, madam.
Bye.
Bye.